First, thank you to everyone for coming to the second virtual workshop on double categories. We're really excited to be hosting this event again after 2 years ago when we hosted the first edition. It's my great pleasure to introduce Miloslav Štěpán, who will tell us about double categories versus factorization systems. Thank you.
Okay, so can I start, right? Okay, so thank you very much for having me here. Okay, today I will talk about the relationship between double categories and factorization systems. This is based on my paper that has been published in Tech, but there's also some small additions I've made, and yeah, I think we can get to it right now. So first, yeah, I will do a very brief introduction to double categories, and then we can jump straight into some main results. And so that's the first part of the talk, double categories and their correspondence to factorization systems. And in the second part of the talk, I will put the first part into a more broad two-categorical perspective. So I will introduce and recall some two-categorical colimits and so on. So we will see how far we will get, hopefully very fast. So, okay, so let me recall a double category. So it's a structure that consists of objects, vertical morphisms. So let me, okay, yeah, vertical morphisms, horizontal morphisms, and squares. And you have two kinds of compositions. So the horizontal and vertical, you can compose both squares, and you can compose vertical morphisms, and you can compose horizontal morphisms. And each of these compositions is associative and unital. So, and and this is not all. There's also this rule that's supposed to hold, is the middle four interchange rule, which says that if you have a square consisting of four squares like this, it has a unique composite. So let me try this. You can compose them like this, and then the big one, or you can compose them like this and like this, and both composites are supposed to be equal. So there are some special cases. For example, if the objects, vertical and horizontal morphisms, are trivial, then this is just a commutative monoid. Some more elementary examples include categories. So every category is a double category if your vertical morphisms are trivial and squares are trivial, so only identity squares. Another special case is two categories, in which the objects are the objects of the two category, horizontal morphisms are morphisms of the two category, and vertical morphisms are trivial. And the squares, so there are only squares of this form, and they correspond to two cells in the two category. So, and the morphism, so yeah, so a kind of morphism between double categories is a double functor, which is an assignment, which sends basically objects, vertical morphisms to vertical ones, horizontal ones to horizontal ones, and squares to squares. And it's supposed to preserve all kinds of compositions and identities. So, and double categories form a category that I will call double. And yeah, so we have seen, ordinary categories and two categories embed in this category of double categories, and actually in quite a lot of ways. Yeah, so let me now introduce examples that will be like the core examples of this talk. So it will be the double categories of commutative squares. So if we have a category, we can consider the double category of squares, in which, so the objects are the objects of the category, horizontal and vertical morphisms are just the morphisms of the category, and a square in this double category. So there is a square like this in the double category if and only if this square commutes in the category C. And there's also its smaller friend that we will also consider, which is the PB skew, which is the sub double category that consists of squares that are pullbacks. So I think, yeah, and so yeah, as I said, so this will be the kind of key examples that we will encounter. So let me stop at them and study their properties for a bit. So given a category C, so what are the properties, like double categorical properties that this double category of commutative squares has? Well, it is flat, which is to say that given two squares that have the same boundary, then they are equal. So in this case, this is obvious, right? Because square in this double category is a commutative square. So there's like every two such squares are the same. And the other property is invariance, which is to say that if we've got this this kind of shape in which the vertical parts are isomorphisms, then it can be filled uniquely into a square. So in our case, this H tilde is given by this composite. Okay, so let me. Yes, another thing. So as I said, the double category of squares will be relevant, and its sub-double category consisting of pullback squares will also be relevant. So a natural question to ask is like, what properties distinguishes pullback squares from, well, all the other commutative squares? And there's like several ways you can approach this. Like you can approach it in a way that's kind of biased towards the vertical side, or the biased towards the horizontal side. But so the way how I approach it is like not biased in any direction, I would say. So the square is a pullback in this double category if and only if it is what I call bottom right bicartesian, which is to say the following. So lambda is bottom right bicartesian. So lambda is here, and it says that given any square like this, there exists a unique square such that this equality of squares holds. Like, yeah, so what I didn't say, like this alpha has to share the bottom right part with lambda. And if you think about it, like in the double category of commutative squares, like this is precisely the pullback condition, right? Because in the double category of commutative squares, any square of this form, it is automatically forced that this theta is equal to the theta that I decorated with bullet. Like, yeah, of course, in a general double category, vertical morphisms don't have to be the same as horizontal ones, so that won't be the case. But for commutative squares, this square forces them to be equal. And as I said, so this reduces to just the ordinary property of pullback square. Yeah, so let me, yeah, so this is another thing that would be useful for my agenda in the further, later part of this talk is some kind of a joint monicity. So, right, recall that if you have a pullback square, the pullback projections are jointly monic, which is to say that given two arrows into the pullback, and these conditions are satisfied, then these two are equal. So the question is how to say it double categorically. The way that worked for me in my paper was the following. So we say that top left corner like this is jointly monic in a double category if for every squares kappa 1, kappa 2, and yeah, for every squares like this, it holds that if these are equal, then these are equal. Yeah, again, let me reemphasize that, right, so these two are kind of a different breed in a general double category. In a double category of commutative squares, this will be equal. So this is how I capture joint monicity. Okay, so we can get right to the one of the key parts of this talk, which is the comparison of strict factorization systems and double categories. Okay, wait, let me start the timer so I know exactly where I am. Okay, so what is a strict factorization system? It consists of two subcategories of a category with the property that every morphism factorizes as a morphism followed by as a morphism from E followed by a morphism from M. And this factorization is unique, not unique up to an isomorphism, but unique on the nose. Okay, and if you have two strict factorization systems, we can define a morphism between them, which is like the natural thing you would think would be a morphism. We define it just to be a functor between the base categories that preserves both of these classes. And this way we obtain a category that I denote SFC, as strict factorization systems. Okay, now I will tell you some examples of strict factorization systems. First of all, there's an important special case. If C is a monoid or a group, this is what's called a Zappa-set product in group theory literature, I guess. And an example is given by invertible matrices. For example, the QR decomposition of matrices. Every invertible matrix can be uniquely written as a upper triangular matrix with positive elements on the diagonal followed by orthogonal matrix. So, yeah, so another example is the product of two categories. So if you have categories A and B, the category C, which is their product, admits a strict factorization system where the first class consists of those morphisms in which the second part is the identity, and in the second class is the other way around. So this is a strict factorization system because, like, clearly every tuple of morphisms factorizes like this. This one is a little rare because actually if you switch the order of E and M, it's still a strict factorization system. This, of course, doesn't happen in other examples. So, yeah, another example is you can take sets, right? Sets and functions, and you take the first class to be surjections and the other class to be subset inclusions. So not injective functions, but subset inclusions. And this is a unique factorization. Okay, I will mention some facts about strict factorization systems. First of all, one like immediate property is that in a strict factorization system, if you take the intersection of these two classes, you obtain just the identities of C. So yeah, so if you are wondering what's the relationship between orthogonal factorization system, so strict factorization system is like almost never an orthogonal factorization system. And it's also an evil notion because something equivalent to a category with a strict factorization system like doesn't need to have a strict factorization system. Okay, so there's some more interesting facts. So why strict factorization systems are, I think, interesting. So if we right, so you know that categories can equivalently be described as monads in the bicategory of spans. And in this correspondence, like the strict factorization systems correspond to distributive laws. And I guess yet another way to describe them is they are strict algebras for the squaring to monad on the two category of small categories. So this is another hint why it's an evil notion, because if something is equivalent to a strict algebra, it will not in general be a strict algebra, but only a pseudo algebra. Okay, so now let me tell you how to turn a factorization system into a double category. So, okay, so this construction is quite general. So if you have a category and two wide subcategories, E and M, by wide I mean that they contain all the objects of C, we can construct a double category of, okay, I will call it, I guess, just a double category of commutative squares. So this is a double category in which objects are the objects of C. Morphisms are morphisms of M. Sorry, the horizontal morphisms are of M. Vertical morphisms are morphisms of E. and squares are just commutative squares. So this is a square in the double category if and only if this commutes. And again, this is this is again a flat double category, for example. Okay. Now, given a strict factorization system, let us think about like what properties does this double category of commutative squares have. It turns out like that every top right corner in this double category can be uniquely filled into a square. And this is because we can just take this morphism M followed by E. This is a morphism in C, and it admits a unique EM factorization. And this unique factorization gives a unique square. And it turns out that this property actually fully characterizes those double categories that actually come from a strict factorization system. So all is, I guess, quite elementary. And yeah, so in my paper, I call these double categories codomain discrete. So a double category is codomain discrete if every top right corner admits a unique filler. And the reason for this terminology is that the codomain functor, like if you know, is the functor that sends, for example, the square to this component, and this codomain functor is a discrete of fibration. So that's I call them codomain discrete. And we denote by codescent the full subcategory of double categories. And now the fact is that this D functor that sends a strict factorization system to commutative squares, it's an equivalence of categories. And I will show you, I will describe its equivalence inverse explicitly. So in the other way around, let's assume we have a codomain discrete double category. We can construct the category of corners. So this is a construction originally done by Mark Weber in his paper on internal algebra classifiers. And it proceeds as follows. So this category has the objects of X, and morphisms are bottom left corners. So tuples of a vertical morphism followed by horizontal one. In this category, the identity morphism is the corner that consists of two identities. And how does the composition work? So let's consider if you have two corners like this. We just looked at this place, and this can be uniquely filled into a square by the definition of the double category. And the composition is just, you just take these two components. So that's your composition. And it's very, very easy to prove that it's a category and so on. There are some properties. For instance, this category admits a strict factorization system, which is like again immediate to prove. Where the first class is these I call these vertical corners, and this one the horizontal corners. And like every morphism can be factored by the vertical one followed by horizontal one, and this factorization is unique. Another interesting property of this construction is that squares in the double category turn into commutative squares in this category of corners. Right. So if you have a square, then a square in the double category, then this diagram commutes. And right. So by this I denote the morphisms in the category of corners. So this is like the morphism whose vertical component is the identity, and horizontal component is M. And the reason why this holds, again, it's immediate. So we just write down this composite, so which is this one. And if you compose them using the square alpha itself, and this gives you this part. So, and moreover, this category of corners is the best category that has this property, and but we will get to it later. Okay, yeah. So, and this gives you a functor. You can turn these codomain discrete double categories into strict factorization systems, as I've just shown you. And like the theorem is that these they are equivalence inverses to each other. So strict factorization systems are equivalent to certain double categories. Okay, so that's all from the strict factorization system part. Now we will improve it or modify it to orthogonal factorization systems, which is a little more involved, but I guess it's still quite elementary, I believe. So let me recall everything. So in an orthogonal factorization system on a category, you again have two subcategories that have these two properties. So again, every morphism factorizes as morphism from E followed by the one from M. But now this factorization is not unique. It's unique up to an isomorphism in the sense that if we have a commutative square like this, there exists a unique morphism between them. So this is the first property. And the second property is that the intersection of these two classes is precisely the isomorphisms of C. And we again have a category that I denote OFS, where the morphisms are the orthogonal factorization systems, and the objects, and morphisms are again functors that preserve both classes. And an example is so there's like overabundance of examples in category theory, but for example, you can take the category of sets, and the first class surjections, and the second class you take injective functions. So this time this is an orthogonal factorization system. And in fact, from the previous section, any strict factorization system can be like improved or modified and turned into an orthogonal factorization system if we put, so we define it as follows. We create these two new classes, E tilde and M tilde, as follows. So this, we just add these isomorphisms here. And this thing is an orthogonal factorization system. Wait. Okay, so let me now again think. So let's start with an orthogonal factorization system now, and let's think about what properties does the double category of its commutative squares have. So first of all, every top right corner can be filled into a square. Why is it the case? Is because again you can take this composite in C and you factor it by E followed by M. But the point is now this factorization is no longer unique. So that's the big difference. So this is the first property. The second property is actually, so is this property. So what does it say? Every square is top right by Cartesian, and this means the following. So this square is top right by Cartesian if we have any other square that shares its top right corner with it, then there exists a unique row. So like this. And so why is this the case? It's because in this double category of commutative squares, this theta bullet is forced to be inverse to theta, and theta is isomorphism, and it ultimately holds because the factorization is unique up to an isomorphism. So earlier I've shown you that pullback squares have some property, and this is vertically dual to the property that pullback squares have. So that's the intuition for this. Like it's vertically dual to pullback squares. Okay, and the third property is the invariance. We have seen this for the category of all commutative squares. So if these two are isomorphisms, I would like this to admit a unique filler into a square. And this is in the case of this double category of commutative square. This is the case because this composite, okay, it's a morphism in C, but we would like it to be a morphism, to be a horizontal morphism, which means a morphism in M. So the question is if it does belong to M, and the answer is yes, it does, because these two are isomorphisms. So that's why they belong to M, and this one belongs to M. So does this composite. So this is another property that this double category has. And the last one is, I think, it's a bit technical, but the point is, like, every corner in this double category, which is obtained from the double category of commutative squares by reversing the directions of vertical morphisms. So this is the vertical dual. And the key property is that every top left corner in this dual is jointly monic. And the reason why this is the case, it again follows from the uniqueness of factorizations. Like if we have two morphisms, theta and tau, and they make these two commute, then they are equal. And it turns out these four properties exactly characterize double categories that come from orthogonal factorization systems. So this is why I call them an orthogonal factorization double category. So it's a double category in which, like, every top right corner can be filled into a square. Every square is top right bicartesian, which, as I said, it's like a vertical dual to being a pullback square. Another property is the invariance. And the last property, as I said, is the joint monicity, which is, like, I guess, the most painful or technical condition, I think. And I denote the category of these double categories by fact double, and I define it to be a full subcategory. And the fact is that this D functor is an equivalence of categories if we regard it as a functor from orthogonal factorization systems to factorization double categories. And what I will do, I will again describe the equivalence inverse explicitly. So this will be again some kind of category of corners, but this time it's more complicated in some sense. So if you have a double category that satisfies the points 1 and 2 from earlier, so this is every corner can be filled into a square, and every square is like some kind of vertical opposite pullback, then we can construct the category of corners again. But this time the objects, the objects are again the objects of X, but this time the morphisms are only equivalence classes of corners. And the identity morphism is the equivalence class of the identity corner. So these are equivalence classes, and the equivalence of two corners, so two corners, EM and E prime and prime, are equivalent if there exists a square beta between them like this. So we can imagine it like a two-cell going from this one to this one. Such a square beta is necessarily unique and also invertible, both vertically and horizontally. And the composition works similar way as before, except now this square is no longer unique. So you need an axiom of choice to choose a square and fill it, and it's independent of this choice, I guess. But I think you need to choose it. You need to choose it, but show it. It's later going to be independent. Okay. And actually, so orthogonal factorization systems are more widespread. So we can hope that these factorization double categories are also more widespread. So let me give you some examples that I believe are quite natural. So if you have a category with pullbacks, consider the double category of pullback squares, except consider its vertical opposite. And you will see why in a second. So, and you can do the category of corners constructions for this double category. So this one has the properties that enable the category of corners construction because all the squares are pullbacks. And in this case, the category of corners has the objects of C. The morphisms are equivalence classes of, so these are like some kind of spans, right? So this one goes in the other way because we take the dual. And the point is, like, if two corners in our definition are equivalent in the equivalence relation, you can see that this happens if and only if like this theta is equal to tau. So these are these components. And this is more of an isomorphism, right? So because so there exists a pullback square like this if and only if like both components are isomorphisms. Yeah, and yeah, so my point is like these two corners are equivalent if and only if there's an isomorphism of spans. So in other words, this category of corners construction, what it produces is the category of spans. Yeah, so that was my point. So okay, another example, we can take yet a smaller cousin of pullback squares, which is a double category M pullback squares, in which I take the vertical morphisms to be monomorphisms. And in this case, the category of corners construction produces the category of partial maps. So partial maps in C. So a partial map is usually defined as an equivalence class of spans like this. So it's yeah, I guess so. So this is like the domain of a function, but the function is only defined on this smaller subset, like in sets at least. And the map is called total if it's like if this is defined everywhere. So this is expressed by this identity here. Okay. Okay, there's another example. You have this double category BOFIP. I haven't introduced earlier, but I will introduce it now, where the objects are small categories. Horizontal morphisms are discrete fibrations. Vertical morphisms are functors that are bijective on objects, but we need to take the opposite again. Oh. And the squares are commutative squares. And actually, it turns out in this case, every such commutative square is a pullback square. So you can proceed with the corners construction, and you can see that in this case, you obtain the category of small categories and cofunctors. And yeah, this is because like every cofunctor can be presented as a span like this. Okay, so that's another. Okay, so if you have a double category, which is a factorization double category, the category of corners admits these two canonical classes again, is EX and MX, where this one is spanned by equivalence classes of vertical corners. So the horizontal component is the identity, and this one has the vertical component, the identity. And the claim is that if this is a factorization double category, then this is an orthogonal factorization system on the category of corners. Why this is the case, I will not tell you the proof, but I will tell you why you need every single of these conditions of a factorization double category. Well, the first two properties, this filling corners and top right bicartesian squares, they are needed to construct the category. So you cannot do without. Now this invariance property, it's used in the proof to show that the intersection of two classes is isomorphisms precisely. And this, I guess, the most technical and annoying condition of joint monicity, it's used to prove that these classes are strictly orthogonal. Without it, they will only be like weakly orthogonal. So there will not be unique fillers. Okay, so yeah, and like the theorem is that this functor D is an equivalence, and this category of corners is again its equivalence inverse. So orthogonal factorization systems correspond to factorization double categories. And there are some examples. Yeah, so ideally, you would like to have some well-known system here and some well-known double category here. I guess if on one side you can get the mono pullback squares where the vertical morphisms are monos, and this corresponds to an orthogonal factorization system on partial maps, or you have the double category of bijections on objects and discrete fibrations, and this corresponds to cofunctors, and they also have an orthogonal factorization system. There's also an quite, I guess, interesting non-example. If you take the pullback squares, here is supposed to be V because you take the vertical opposite, but if you take all pullback squares, then this corresponds to spans, as I've shown you, but spans, it doesn't have an orthogonal factorization system. And the reason why is that this one doesn't have the joint monicity property, because not every corner here is jointly monic. The ones that correspond to pullback squares, they are jointly monic, but not every corner corresponds to a pullback square. So this is kind of the reason. Okay, so this is, I guess, the end of the first part. Okay, so I have a lot of time, so I think I can start. Unless there are any, have there been any issues so far with my recording or anything? Okay, okay. So I will continue with this second part. So yeah, as I said, so the goal of this part is to like put these results above that are quite, I believe, elementary, to put them in like some wider perspective of two-category theory. So let me recall some simplicial notation first, which is unfortunately unavoidable. So I will just denote this N to be the category of, yeah, so this linearly ordered category of ordinals, or yeah, this ordered set, and I will regard it as a category. And I will also define by delta 2 this truncated simplicial category, where I only consider these three objects. So these are the ordinals of sizes 3 to 1. And here I use the simplicial notation where by these maps, I denote, so these maps have the defining property that if the bottom index is J, then the fiber over J is empty. So this is an example of this delta 1, which is this one. So this is the delta 1. It omits the middle one. We have a canonical functor. Yeah, as I said, I regard this as categories, so we can embed it into cat, the two category of small categories. And the diagram like this is referred to as a coherence data. And the colimit of this diagram, weighted by this W, is called the codescent object. So yeah, so the codescent object, it's kind of a high dimensional analog of coequalizers, and also there are many parallels, like for example, you know, monadicity theorems, they use coequalizers, and if so the higher dimensional ones, some pseudo monadicity theorems, they use codescent objects, and there are many examples like this. But we will, so what will we do? Yeah, one example of coherence data is if D is a small category, it gives you this truncated simplicial object or this coherence data in sets. So this D0 is the set of objects, this is a set of morphisms, and this is a set of composable pairs of morphisms. And this one sends morphism to its target, this one sends it to its source, and so on. And we can consider this diagram to live in cat. So yeah, so this is the diagram of sets, but we can embed it in categories if we regard each of these as a discrete category. Okay. Another example, which is the key example, is if X is a double category, it gives you coherence data in cat. In this case, this X0 is the category of objects and vertical morphisms, and this X1 is the category of horizontal morphisms, which is the objects of X1, and morphisms are squares. And this D0, D1, they are the domain and codomain. So for example, this D0 sends a square like this into this one, and so on. And yeah, so alternatively, you can define double categories like this as some category object in cat. But what you can prove is that if you have a double category and you regard it as a diagram, then the cocone for this diagram actually can be described as just a pair of functors like this. So by this thing, I denote the category of objects and horizontal morphisms of the double category. And this is the objects and vertical morphisms of the double category. And the cocone can be described as a pair of functors like this that agree on objects. And moreover, every square in this double category turns into a commutative square in C as follows. And this is a colimit cocone. If for any other cocone, there's a unique map like this. And now we can define a category that I call cocone for reasons that will become, well, already from some. So I define a category that it will be like the category of cocones for double categories. So it's a subcategory of these cospans whose objects are pairs of functors that agree on objects, and moreover the objects of V and H are equal. And morphisms in this category are just triples like this, making everything commute, and also agreeing on objects. It's not entirely important, but what's important is that we can do again the double category of commutative squares, but this time it's generalized. This time these do not have to be inclusions. They can be any functors whatsoever. And we can define this double category df psi such that the objects are the objects of P, horizontal morphisms are from A, vertical morphisms from H, vertical morphisms are from V, and squares are commutative squares. Now what you can do, you can prove that there's an adjunction like this, where this D, we have just seen it, it sends a cocone into the double category of commutative squares. And the left adjoint, it sends a double category into its colimit cocone. And we have seen the colimit cocone, just as any cocone of a double category, is an element of this one. And the point is, and this one is done using the codescent object. And now what can be also seen is that this adjunction actually restricts to all the equivalences we have seen. So this restricts to strict factorization systems and domain discretes, orthogonal and factorization double categories. What's also interesting is that it restricts to weak factorization systems. But my kind of issue, or I guess I stopped working on it sometime, but this also restricts to certain class of double categories, but I haven't been able to capture these ones like using elementary terms. So maybe it's also similarly easy to these ones, but I haven't been able to do it. I still have a few more minutes, so let me say some additional things. Yeah. So we can see that the category of corners construction I've shown you before is actually a colimit of the double category if you regard it as a diagram. So I have it here explicitly. If you have a double category that satisfies, for example, these two properties of the bicartesian and filling corners, then we can consider these two embeddings. And you can see that this is the codescent objects of X, which I think it's kind of, so an explicit example, let's come back to it again. Let's consider the pullback squares again. I've told you that the category of corners is spans. And because it's a category of corners and it's a colimit, it enjoys a universal property, which I find, I haven't seen it anywhere else. So for example, for the spans, it says the following. So if you have a category with pullbacks, any pair of functors like this that have the property that pullback square in C turns into a commutative square in E, then there is a unique functor from spans that has this description. So this you can kind of, and you can also replace spans by partial functions or the cofunctors, and they have universal properties like this. So these are kind of interesting additional tidbits. So another tidbit is the fact that this adjunction can be seen to be idempotent, and as such generates an idempotent monad on double categories. And what I find interesting is, I guess, if X is a double category, then what this T tilde does, it flattens it. So this double category is always flat. But it is not the case that every flat double category is of this form. So we can consider this pinwheel, this double category freely generated by this graph, which is coincidentally also the logo of this workshop. And you can see that this double category doesn't have the, like, there's no composite, there's no composite for this diagram. There's, like, you cannot compose anything here. But, and the point is that this double category is not of form T tilde of X, because if it was, it would be like isomorphic to T tilde X, which would not happen because T tilde X is a double category of commutative squares. So, like, and the point is, like, this, if we do the category of corners, this big square commutes, so it would be present in T tilde X, which it's not here. So what I suspect is, like, this T tilde X is like the best thing you can do to a double category to make it admit these kinds of composites, but I haven't proved anything of this sort. Yeah, so there's actually, I can say just 2 words on it. These category of corners constructions have been introduced by Mark Weber to study, like, some internal algebra classifiers, which is related to Lex morphism classifiers. And I can tell you just very briefly the story for monoidal categories. Any strict monoidal category, like, gives you some kind of double category, and you can see that this double category, or the transpose of it, is codomain discrete, and you can compute its colimit using the category of corners. And the point is, like, from some abstract theory, two-dimensional monad theory, it follows. Yeah, I have explicit prescription here. It's not important, but what's relevant is that this, in this case, it has the property that any Lex monoidal functor can factorize it through a strict one. And so this is kind of the usage of the category of corners in this context. And, like, the same story holds for Lex functors or Lex double functors or Lex natural transformations. So, yeah, in case of Mark Weber, he used the category of corners to compute, like, for example, was the best universal, or was the best symmetric monoidal category containing a commutative monoid. And to answer questions like this, he used the construction. Okay, so I think I can finish with this, like, last thing, which is, like, if X is a general double category. So the category of corners I've shown you, it only applied to some special cases of double categories, but if X is a general one, you can generalize it in terms of generators and relations like this. So what's the formula for the codescent objects? It's some generalization. So it's again, I denote it again a category of corners. The objects are the objects of X, but this time the morphisms are not corners of length, like, 2, but it's general paths. So it has any finite length, and it's an equivalence. So you take the equivalence relation, and the relation is generated by these rules. So again, existence of a square, you would like these 2 paths to be identified. You would like these composites to be identified if both are vertical or horizontal. And again, you would like this identity to reduce to nothing. And there are some examples. Let me just, I find this last one interesting. It computes the category of fractions, or inverts every morphism, but it's not that important. So there are some last things I would like to mention. That the first question, I don't know if I would be happy if maybe someone from the audience had any, for example, some idea. So I haven't encountered any double categories that are not flat in which had bicartesian squares. So all the bicartesian squares are in flat double categories. So that's the one question. There's some other question that's important, but yeah, again, so there's, like, more questions one can ask. For example, given an orthogonal factorization system, like, does this double category have any double categorical colimits, for example, and what does it mean for the orthogonal factorization system? So I also do not know. But I guess the question I find the most interesting would be to be able to describe this double category that comes from a weak factorization system using some elementary double categorical properties. As I said, I haven't done it. There are some references. So the first one is my paper that's in tag. The second one is my thesis that's just been finished a few days ago. I think it's not available yet. There's some additional thing, but the most of it comes from this paper. And the last reference is the paper of Mark Weber that introduced the category of corners construction. Yes, so I guess that's all. So thank you very much for your attention.
Thank you very much. Okay. What I'll do now is we have perfect timing, by the way. We have time for questions. So I'll allow people to unmute yourself. And if you have a question, you can either raise your hand or just unmute and go for it.
Hello, Milosh. Thank you for the talk. Do you know what are pseudo-algebras for the squaring to monad? Are they also some kind of factorization systems?
Yes, the normal pseudo-algebras are orthogonal factorization systems. That's right. But I haven't, that's right. But I haven't pursued it any further. There are also some the Lex algebras are also something, and it has been studied by Rosicki and I think Tolen. I'm not sure.
Have you thought about trying to characterize algebraic weak factorization systems in this?
Yes. Well, I haven't. Well, in the paper there is a special case if the algebraic weak factorization system is a double category, and if you compute its codescent object, you obtain the category of weak maps, as studied by Borg and I think Garner in their paper. So there are definitely some connections, but I haven't tried to characterize them, but it might be interesting. That's right. Yeah.
I guess I have a question which isn't very well motivated, but kind of comes from simplicial theory stuff, which is, have you studied what happens if you take these codescent data diagrams and you only look at you throw away the morphisms that go from x0 to x1 and x1 to x2. You only look at ones that decrease the index. So you get something like semi-simplicial. Because normally these guys give something that's sort of weakly equivalent. So I was just wondering if you've looked at any sort of generalizations like this.
So you would consider like this thing, for example.
Exactly. Yeah. You don't look at the maps in the other direction.
No, I haven't ever needed it, but well, but as far as for example the formula of the codescent object, it should be very straightforward. You just do not have the identities, so I think, yeah.
Okay, cool. Thanks.
I also had a question. You had these full subcategories of the category of double categories and double functors that you defined. Is there any hope that these full subcategories are reflective or co-reflective?
I'm not sure. For example, the Well, this should be, I guess, the first thing to think about this one, right? And I'm not sure. I haven't thought about it, but it might.
Okay, thank you.
Yeah.
We have time for some more questions if there are any further questions.
I have a quick.
Are you connected to audio? Yeah, I think so.
Is that better? Okay. Yeah, I have a quick comment. First of all, thanks for the talk. It was very interesting. The description that you gave of the codescent object of double categories I found particularly interesting because it's kind of like a midway point between the funny tensor product and the Cartesian product of categories with the same object, because the double cells kind of seem to mediate when you want squares of that form to commute. So I found that particularly interesting. But yeah, I thought that was a nice perspective offered by codescent objects of double categories. So yeah, thanks for the talk.
Okay, thank you. Yeah, I've arrived at that description. It's any codescent object can be built using co-inserters and co-equifiers. So this is what you arrive to it. Yeah, and for example, if you take the double category which has no non-identity squares, then the codescent object is like if you take this, the codescent object of the vertical and the horizontal, it's actually a push out, for example. So that's some interesting and funny thing. But...
Okay, if there's no further questions, let's thank our speaker again.